All right, let's just dive right in and demystify the somewhat intimidating world of fine-tuning large language models. Look, if you've ever felt completely overwhelmed by all the dense AI jargon out there, you are absolutely in the right place. In this explainer, we're going to translate some highly technical machine learning concepts into everyday, relatable analogies. By the time we wrap up, you won't just know what fine-tuning is on a surface level. You're going to understand exactly how it works, under the hood.
Just to keep us perfectly on track, here's our roadmap for today's explainer. First, what is fine-tuning? Second, the AI toolkit. Third, the magic of LoRa. Fourth, mastering the hyperparameters. And fifth, the danger of overfitting.
Okay, kicking things off with Section 1, what is fine-tuning?
So, the absolutely crucial thing to grasp here is that fine-tuning isn't just handing your AI a temporary cheat sheet or a reference document to read over. It is a permanent shift in its core behavior. Think about it like this. If you need some medical advice, you could just hand someone a massive medical textbook and ask them to go search for the answer. Or you could actually send them to medical school for years so they permanently become a doctor. Fine-tuning? That's medical school. It's kind of like teaching a child that waking up early is a good habit. You're permanently embedding that logic directly into their foundational understanding. You're actively, permanently shifting the model's baseline behavior.
Moving right along to Section 2. The AI toolkit.
You know, there's always so much confusion around when to use which AI technique. So let's break down the toolkit. If you have, say, 500,000 pages of company HR policies, and you just need the AI to find two very specific paragraphs, you use RAG, Retrieval Augmented Generation. But the catch with RAG is latency, because the AI has to go actively search a database every single time you ask it something. Now, if you need real-time live data, like checking a bank balance, you'd use tool calling. But what if you want the model to just know the information instantly without relying on any external databases at all? That is exactly when you fine-tune it. Fine-tuning completely eliminates that search latency, and as a huge bonus, it drastically reduces your token costs because you aren't forced to paste massive blocks of context into your prompt every single time.
All right, Section 3, the magic of LoRa.
Now, you might be sitting there thinking, okay, but doesn't fine-tuning require a massive warehouse of GPUs and a PhD in deep learning? And honestly, historically, you'd be right. Trying to manually freeze and unfreeze layers on a 750 billion parameter model on your laptop is literally impossible. But thanks to newer techniques like PEFT, that's parameter efficient fine-tuning, and specifically this thing called LoRa, or low-rank adaptation, the whole game has changed. We can now dynamically update just the strictly necessary parameters and do it incredibly efficiently. In plain English, you do not need thousands of data points anymore. You can actually fundamentally alter a massive LLM's behavior using as few as 20 high-quality examples. It's wild.
And the workflow itself is just incredibly accessible now. If you use a UI like Google AI Studio, this previously terrifying, highly manual process is distilled down to basically 4 super simple steps. Say you want to build a custom caption generator for your marketing team. You literally just create a spreadsheet with maybe 20 examples. The input could be cake company, and the output is a catchy title, a birthday cake emoji, and 2 hashtags. You upload that CSV, you map your input and output columns, pick your base model, something fast like Gemini 1.5 Flash, and set your parameters. And boom! Just like that, the AI learns your very specific pattern.
Which brings us to Section 4, mastering the hyperparameters.
Okay, so right before you hit that tuning button, you have to configure a few settings called hyperparameters. The first one you'll see is epochs. An epoch simply means passing your entire dataset through the neural network one complete time. Think of it like an old-school sugarcane machine. Imagine a stalk of sugarcane is your dataset. Passing that whole stalk through the crusher one time to extract the juice, that's one epoch. But, there's usually still some juice left in there, right? So you fold the sugarcane in half and pass it through a second time. That's epoch number 2. You run your data through the model over multiple epochs to extract all those hidden learning patterns and squeeze every single drop of knowledge out of your dataset.
Next up is batch size. Let's say you actually do have a massive dataset. Well, the computer can't process all of that in a single split second. Think about a huge university. If they have 200,000 students enrolled, they obviously can't fit them all into one giant auditorium and teach them all at the exact same time. Instead, they break that massive student body down into much smaller, manageable, classroom-sized chunks. And that perfectly illustrates why we use batch sizes. It's just breaking your massive data set into little chunks, say 4, 8, or maybe 16 samples at a time, so the model can actually process and learn from them effectively before updating its internal weights.
Finally, we have the learning rate. This is all about how your model corrects its mistakes to reach what we call zero loss, or the perfect global minima. Imagine you're trying to step exactly onto a very specific spot on the floor, like right on the threshold of a door. When you're far away from that door, you naturally take huge, fast strides. But if you keep taking those huge leaps as you get closer, you're literally going to step right past it. So, as you approach the target, you instinctively start taking cautious, tiny little steps. The learning rate dictates exactly this, dynamically taking big leaps early in the training when the AI's errors are really high, and then shifting to tiny, ultra-precise steps as the model dials in on that perfect accuracy.
And finally, Section 5, the danger of overfitting.
Okay, so we've got our parameters expertly set, but now we have to face the ultimate pitfall of fine-tuning. What happens if an AI studies too much? I mean, it sounds totally counterintuitive, right? How on earth can an AI study too much? Well, let's look at why running your data through that sugar can machine one too many times actually ruins the juice entirely.
In machine learning, it's a super delicate balance. If you only run your data for a single epoch, just one pass through the machine, your model will probably suffer from underfitting, which is also known as bias. It's exactly like reading a ridiculously complex math textbook just one time the night before a final exam. You might grasp the basic concepts, but you're going to completely fail the hard questions. You just lack the capability. But if you swing the other way and run the data for, say, 100 epochs, you trigger overfitting, or variance. Overfitting is pure, mindless, rote memorization. It's like reading that exact same math book 100 times until you memorize the exact answers to the specific questions in the book. Sure, you'll score 100% in your training, but the very second the real world asks you a brand new, slightly different math question, you fail spectacularly. Why? Because you didn't actually learn the logic, you just memorized the text.
There's actually a hilarious, but honestly highly accurate real-world example of this. Let's call it the shoddy.com problem. Imagine you fine-tune an AI for a matchmaking or dating app, but your training dataset happens to only consist of profiles of wildly handsome, super smart millionaires. The model is going to completely overfit to that incredibly specific criteria. It will just assume that only handsome millionaires are acceptable matches. As a result, when you deploy this shiny new AI into the real world, it's going to blindly and instantly reject every single normal, average person's profile it sees. Overfitting causes the AI to become horribly, rigidly biased to whatever was in its training data.
It totally reminds me of how people talk about those classic rote learning students. You know, the quote, "The brains of our top students are overfitted on textbooks. They can repeat the book verbatim, giving off this amazing illusion of genius. But because they didn't actually absorb the underlying logic, they can't adapt to new patterns or solve novel problems." And this humorous reality perfectly captures why an overfitted AI might look incredibly smart on your testing graphs, but then completely fall apart the second a real user types something slightly unexpected. Look, fine-tuning gives you this incredible, permanent control over an AI's behavior. It lets you turn a generic chatbot into a highly specialized expert. But, as they say, with great power comes great responsibility, especially for the quality of your data. So, as you venture out and start fine-tuning your own models with awesome tools like LoRa, and as you're carefully tweaking those epochs and batch sizes, just keep this one final question in mind. Are we actually teaching our AI to think and understand? Are we just hard-coding it to perfectly memorize our own biases?